today's session, we'll continue our journey into tokenization, which is a fundamental step in processing text for NLP tasks. In the last session, we explored key NLP tasks like name entity recognition, sentiment analysis, and summarization. And we saw how tokenization is a starting point for many of these tasks. Today, we will build on that foundation and cover advanced tokenization techniques. Specifically, we will look at word level, character level, and subword level tokenization. We will explore methods like byte pair encoding BPE, word piece, and sentence piece, which are used in modern NLP models like BERT and GPT. And as always, we will get hands-on experience by experimenting with these tokenization methods on real datasets. This session is essential for understanding how to prepare text for NLP models, especially when dealing with large corpora or rare words. So let's get started and dive right in. Hello and welcome back. In today's session, we'll continue our journey into tokenization, which is a fundamental step in processing text for natural language processing tasks. Here is the outline of what we'll cover in today's class. We'll look at tokenization techniques, including word level, character level, and subword level tokenization. Specifically, we'll look at subword level methods, including byte pair encoding BPE, word piece, and sentence piece. And as always, we'll have a hands-on experiment with these tokenization methods on real datasets. So by the end of today's session, we'll be able to understand the importance of tokenization in NLP, be able to differentiate between word level, character level, and subword level tokenization methods. Should also be able to explore and implement subword tokenization techniques, including BPE, word piece, and sentence piece, and also understand their real-world application. And then we should be able to apply these methods to prepare text datasets for training NLP models. Let's begin by understanding what tokenization is and why it's so important in natural language processing. Tokenization is the process of splitting text into smaller manageable units, what we call the tokens. And these tokens usually represent words or subwords or even individual characters, depending on the task and the method used. And this step is very crucial because machines can directly understand raw text. So if we break the text into analyzable components, the tokenization method prepares it for further processing, making it easier for models to work with this particular type of data. So once we have the tokens, they are converted into numerical representations such as word embeddings or indexes. And then these formats are required by machine models to make predictions or learn patterns. Tokenization isn't just about splitting text. It is about deciding how to split it based on the specific needs of our task. Let's take a look at this very simple example. So we have a text that says, let's tokenize, isn't this easy? So, and we have a tokenization rule here. In this rule, we use predefined linguistic rules to break text into tokens. For example, contractions like let's in English language could be split into let and then apostrophe s. And here we are recognizing both the components as being meaningful. And then you can have others, for example, tokenizing on punctuations, where punctuation marks like exclamation mark, question mark, etc., serves as delimiters. You can also have tokenization on white spaces. Okay, what we have here. So this is actually the simplest policy. and it splits the tokens wherever there is a space. So in this our text that we have here, wherever there is a separation based on a space, then that particular word is tokenized appropriately. So we have let's tokenize isn't this easy. However, this approach doesn't handle punctuations or contractions effectively, as you can see. So basically, choosing the right policy depends on the task you're working on. For example, white space tokenization is faster, but may mean certain nuances like contractions, while on the other hand, rule-based tokenization is more accurate but can be computationally expensive. So at a broad level, there are three types of tokenization in NLP. There is what we call the character level tokenizer, there is what we call the word level tokenizer, and there's what we call the subword level tokenizer. So the word level tokenizer, as you can see here, tokenizes the given text at word level. So for example, we have I love NLP. Here it is tokenized into I love NLP, treating every word as a separate token. For the character level, it treats every character as a token. And then for the subword level, it's like the middle ground between the word level and the character level. So it breaks the text into subwords. For example, we have unbreakable here being broken down into on, break, and able. And this is crucial for text pre-processing in machine learning models. So let's start with the first one, which is the word level tokenization. It's actually one of the most common and straightforward tokenization method in NLP. And it works by splitting a given text into individual words or tokens. For instance, the given sentence here, grew a pretty little factory, etc., could be tokenized into individual words, as we can see. However, while it is simple and effective for many tasks, word-level tokenization does have a limitation. And this includes struggling with unknown words, or different word forms, for example. We will explore some of these challenges and how to overcome them later in this session. While word-level tokenization is simple and widely used, it does come with a few challenges. The first challenge is what we call the out of vocabulary words. And these occur when the tokenizer encounters rare or unknown words that don't exist in its vocabulary. For example, in the sentence, natural language processing with Hugging Face, the word Hugging Face may not have been seen during training, and this can make it difficult for the model to handle. So this is what we call out of vocabulary words, OOV. Another challenge is the vocabulary size. To cover all possible words in a language, you would need a huge vocabulary, which increases the memory and the computational requirements. And this is especially challenging for languages with large vocabularies or languages that have diverse forms. Another challenge is ambiguity. Word-level tokenization can fail to distinguish between different meanings in a compound word or a phrase. For example, the word ice cream refers to a dessert, isn't it? But if we tokenize it, it is going to be tokenized as ice and cream, isn't it? Which loses its context, isn't it? So these challenges highlight the limitations of word-level tokenization and why advanced techniques like subword tokenization have been developed to address these issues. We're going to come to that later. Before we come to subword level tokenization, let's look at character level tokenization, which takes a different approach by breaking text into individual characters as opposed to individual words. For example, in the text, "Isn't this nice?" Okay? The character level tokenization would produce tokens like each character separately, isn't it? Depending on the rule we're using, isn't it? If we're adding special space symbol, then we're going to have a special space symbol after each and every character. Or if we're ignoring some symbols, then we'll simply have the characters themselves. Okay? Or if we want to tokenize all characters and symbols, then we can have even the symbols tokenized as characters separately. So as you can see from here, each and every character is tokenized separately. So this method processes every character and symbols in the text and makes it useful for language that have no clear word boundaries or when you're dealing with unknown or rare words. Character level tokenization captures fine-grained details. However, it results in much longer sequences, which can increase the computational cost. Character level tokenization is particularly useful in specific scenarios. For example, languages without clear word boundaries, like Chinese or Japanese. Okay? In these languages, words are not separated by spaces, and therefore breaking text into individual characters provide a practical way to process this type of languages. Also, instead of treating an unknown word as a single out-of-vocabulary token, character level tokenization represents it as a sequence of its own constituent characters. And this ensures that the model can still process and learn from the word structure. Character level tokenization is commonly used in tasks like character level language models, where predictions are made at the character level, or sequence to sequence tasks such as machine translation, where every character in the input sequence is transformed into an output sequence. So although this is a versatile approach, it does lead to longer sequence and also requires more computational power, which can be a trade-off depending on the task that we are considering. So while character level tokenization has its advantages, it also comes with significant challenges. The first challenge is loss of context. Yeah, because characters alone lack any semantic meaning. For example, if you break the word cat into C, A, and T, that doesn't provide any information about the word's meaning. So models must work harder in order to infer relationships and context from such granular data. Another challenge is increased sequence length. Character level tokenization generates longer sequences compared to word level tokenization. And this increases the computational cost, especially for large datasets. And that's because models have to process more tokens. Another challenge is the complexity in modeling. Models must learn both low-level character patterns as well as the high-level word-level structures in order for them to effectively interpret the data. And this usually adds complexity and will require larger datasets and more training time to achieve good results. So despite these challenges, character level tokenization remains very useful for specific tasks like handling rare words or processing languages without clear word boundaries like Chinese or Japanese. So in order to handle this increased sequence length and the granular input of character level tokenization, we often require a special process to handle this. And this basically involves pooling or aggregation before the characters are passed to the deep neural network layers of the model. And here is how it works. The input text is first of all broken down into individual characters. with each character represented as a vector. And then these characters are passed as a vector to a deep learning language model where we apply the pooling layer. The pooling layer aggregates the information across the characters. The pooled output is then transformed into an embedding vector for further processing in the model's layers before finally passing the aggregated embeddings to the output layer. And this is where the final predictions or the classification task is performed. So let's now look at subword level tokenization, which, like we said, is a balance between the word level and the character level tokenization. And in this case, instead of breaking text into full words or single characters, what happens is that this approach splits words into smaller, meaningful units called subwords. For example, like we mentioned earlier, the word unbreakable might be split into on, break, and able. So what's the key advantage? Subword tokenization is particularly effective for handling unknown or rare words. So even if a word isn't in the vocabulary, its subwords are likely in the vocabulary. Okay? So, and common subwords like ing, un, able, etc. that appears as prefixes and suffixes in most words are shared across multiple words. And this can significantly reduce the vocabulary size while retaining useful information. For example, let's look at the word any place. Any place is a single word. So as opposed to splitting it into characters, and of course, because there are no space here, we don't want to split into words. So we can break this particular word into any and place. And this approach not only aids in handling out of vocabulary words, but also reduces the model's size and improves efficiency. And one good thing is that these tokenizers are specifically designed to address the challenges of OOV words, and they do that by breaking down words into smaller units. And this enables the model to be able to handle a broader range of vocabulary. Now, subword level tokenization methods include byte pair encoding, word piece tokenization, sentence piece tokenization, and there are several others including unigram tokenizations, etc. But these three are the ones we will be discussing in this particular session. Let's start with the first one, that's the byte pair encoding or BPE, which works by starting with individual characters as tokens and then iteratively merging the most frequent pairs of characters or subwords in the dataset. And then in doing that, it creates new subwords until a predefined vocabulary size is reached. More formally, these are the steps of byte pair encoding tokenization. The first step is to start with a vocabulary that contains individual characters, and then we identify the most frequent pair of tokens. We then merge them into a single token. We keep on repeating this until the desired vocabulary size is achieved. When working with BPE, the desired vocabulary size is usually a hyperparameter, so you're the one to set it before training starts. For example, let's assume we want a total of 17 tokens in a vocabulary, and then given this particular words and their respective frequencies. So we have the word car occurring 5 times, cable 3 times, tablet 1 time, watch 2 times, chair 5 times, mouse 1 time. As a first step, all the unique characters and symbols in the words are included as base vocabulary. So in this, the base vocabulary would be this. So these are all the individual characters in all of the words. Remember, we've set our vocabulary to be what? To be 17. And here we're starting with 14. The next step is that all the words are split into the base vocabulary characters, which can be represented as follows. So each and every word is represented using the base vocabulary characters. So for car, we have CAR. For cable, so we split each and every one of these particular words into characters. And then the BPD algorithm counts the occurrence of every symbol pair and then picks the one with the highest frequency. Okay? For example, in this particular example, the pair CA, where we have two words appearing together, CA, occurs 5 times in car. It also occurs 3 times in cable. Okay, and that's making it a total of 8. Okay, and if you look carefully, this is the highest pair that we have in this particular vocabulary, isn't it? It is followed by the word CH. Where is it? CH here, which occurs 7 times. It's appearing 5 times here and appearing 2 times here. Okay, and when we continue doing that and so on, isn't it? Next is that the most frequent pair is added to the vocabulary and all the occurrences of the individual characters are matched. For example, we said the most frequent pair is CA here, isn't it? Okay, CA. So what happens is that you add that to the vocabulary and all the occurrence of the individual characters are matched. So here we have car, as opposed to having CA, we have car, okay? And here, as opposed to having cable, we're having CA. So that's what happens. The next step is to identify the next highest occurrence of a pair. In this case, the next highest occurrence is of the pair CH. So what we do is now to add this particular pair to the vocabulary, and wherever we have the characters C and H, they are merged together. So in this case, our vocabulary will now be the initial 14, which we initialized, and then the previous one, CA, and then plus this one, that's CH. So our size is 16. We continue. And then here we have CAR. Wherever we see CA, we put it as CA, and wherever we see CH, we merge them together, isn't it, as one token. Okay? Do we stop? No, we don't stop because we've not reached our maximum size. So we continue to the next step. So since our target vocabulary size is 17, the byte pair encoding method will choose the next most frequent pair. And if you look carefully, you see that the next most frequent pair is the word CA and R. Remember, CA is now an individual token. So if you count carefully from the 16 tokens we have previously, you see that CA and R is the next pair that's the most frequent, and it occurs 5 times here. Okay, so this means the CA and R will be merged as car wherever we see CA separately and R separately. Okay, and then this will be the resultant vocabulary. So we have A, B, C, E, C, A, C, H, and then C, A, R. And then if you look carefully, if you count, this is our final vocabulary size 17. The final tokenized input will now be car occurring 5 times, CABLE 3 times till we reach the last particular token. And at this point, no further merging will be done since the vocabulary limit has been reached. Now that the byte pair encoding has been trained, the same tokenization merges will be applied to a new word. Let's say, for example, we have a new word here, cab. So it will be tokenized into CA and B because CA and B featured in the final tokenized input.
CA, and then we have B here. However, if we have a new word, let's say card, it will get tokenized into car, and then here the D here is not in the final tokenized input, so we represent that as UNK, what we call unknown. Okay, why? Since the letter D is not in the final tokenized vocabulary. Even though practically this never happens, because all characters occur in the corpus at least one time. However, UNK, what we call unknown, may be encountered if a symbol like punctuation or a number was not added in the original vocabulary but is part of a new word. Byte pair encoding is widely used in models like GPT, where it helps balance efficiency and performance. So if we break down rare words into subwords, the BPE tokenization method reduces the vocabulary size and makes it easier for the model to be able to learn and generate text. It is also heavily used in machine translation tasks because it allows the model to be able to handle a wide range of language and dialects. And it does that by focusing on subword units as opposed to the entire word, which anyway might be missing in smaller training datasets. Okay, BPE also is particularly very helpful when dealing with lot of out of vocabulary words, OOV, or when we are dealing with languages that have complex word formations. Another subword tokenization method is word piece tokenization. It's very similar to byte pair encoding. However, its pairs are usually chosen not using frequency, but by maximizing the likelihood of the training data. So basically, word piece tokenization takes a probabilistic approach to learning subword units. Instead of just merging the most frequent pairs like what is done in BPE, it prioritizes subwords that are likely to appear together based on the likelihood of sequences in a given dataset. One of its key strengths is how it handles frequent words. For example, if a word appears often in its full form, word piece will try to keep it intact as opposed to splitting it into smaller units. And this helps in minimizing unnecessary splits for commonly used words. However, when it comes to rare or unseen words, word piece effectively breaks them down into smaller subword units and ensures that they can still be understood by the model. So this balances between retaining whole words and also breaking down rare words. And this is why word piece is used in modern algorithms like BERT. It's also great for creating a vocabulary that supports both general language use and edge cases like unseen words. The steps for word piece tokenization are as follows. Number one, we start with the base vocabulary of characters. We then iteratively add subwords in order to maximize the likelihood of the data. Finally, we ensure that subwords are meaningful and contribute to compact vocabulary representation. Here is how word piece handles tokenization with words. Let's say we have the input word unbreakable. So the input word unbreakable will be broken down into on, break, and then able. The prefix here, the double hash prefix before break and before able, indicates that break and able are parts of a word that was already split. So it means this break is part of this particular word. So we have on break. And then it's also saying that this able is part of the previous words. Okay, so we have unbreakable. So the prefix indicates that the subwords belong to a previous word. The key advantage here is efficiency, because if we break the words into meaningful subwords like on, break, and able, it can be efficient for us to now be able to do further processing. Word piece tokenization reduces redundancy in the vocabulary. So instead of storing every word separately, the model can store only the subwords that are shared across many words. This reduces the size of the vocabulary, but it also helps in preserving the meaning of the word, even when dealing with unfamiliar or rare terms. This approach makes word piece tokenization to be particularly powerful for tasks like language understanding, where the model needs to handle a wide range of words efficiently without losing context. Word piece tokenization is used in several algorithms like BAT, Albert, and other transformer-based models in order to efficiently tokenize text. It helps manage large vocabularies and ensures accurate representation of both common and rare words, and this makes it to be ideal for language understanding tasks. Another subword level tokenization method is what we call the unigram tokenization. It starts with a full vocabulary of words or symbols, and then iteratively removes tokens with the highest loss based on log likelihood. And its key feature is that it always retains base characters in order to ensure that all words can be tokenized. Another subword level tokenizer is what we call sentence piece. Unlike the traditional tokenizers, sentence piece does not assume that spaces separate words. So what it does is that it processes the input strings in its raw format, including the spaces. And basically it uses either BPE or unigram algorithms to create the vocabulary. And the key feature of sentence piece tokenization is that it treats spaces as tokens by prepending them with this underscore symbol. So it prepends the words with underscore, just to treat them as separate tokens. So the key concept is that it is a language-independent subword tokenizer that works directly on raw text. And this means it does not require any pre-tokenization like splitting on spaces or any of those stuff. This makes it particularly useful for multilingual tasks where language-specific pre-processing might be a challenge. It supports two main algorithms, the byte pair encoding and the unigram language model. And this gives it flexibility depending on the needs of the task. Also, sentence piece tokenization is great for creating compact, efficient vocabularies for models like T5, as well as other sequence-to-sequence models. Sentence piece is excellent for handling multilingual datasets because it doesn't rely on language-specific tokenization rules, and this makes it adaptable to a wide range of languages. It also works well with special characters and different scripts. This ability to work with special characters and different scripts is very crucial for tasks like translation or multilingual text generation, because in this particular task, the input can vary significantly across languages and also different writing systems. This flexibility helps in building more generalized models without the need for separate processing for each particular language. In sentence piece, the input, for example, I just got a phone key from case, would be tokenized as follows. This prefix, this underscore prefix, is used to indicate the boundary of subwords. So basically it's showing that the word I and just are separate subwords. And this boundary marking helps the model to be able to understand where one subword ends and where the next begins. And it really makes it more efficient and effective for tokenizing text in ways that is flexible across various languages. Note that some tokens like KY here may not have a preceding underscore because they are part of a larger word split during tokenization. Okay? Sentence piece is widely used in multilingual models like T5 or MBAT. Its ability to handle raw text, without language-specific pre-tokenization is what makes it particularly useful for this type of models, because they are designed to work across many different languages. Sentence piece ensures that tokenization process is consistent and efficient even when dealing with a diverse range of languages and scripts. It is now time for us to have a practical walkthrough in Python. So we'll start by introducing word level tokenization. Okay, even though we've already seen this in some of our previous labs, but since this is a comprehensive tutorial on tokenization, so we want to start from word level, character level, before we come to the subword level tokenization. Okay, so here I'm assuming that we all have NLTK installed. That's the Natural Language Toolkit, which is the library that we'll be using that provides a set of functions for natural language processing. And specifically, we are going to be using this particular function, word tokenize. It's a specific function from the NLTK.tokenize class that is designed to split any given text into individual words. You also install or download the Ponketi resource. Okay, if you've not done that, please do that. It's required that you go to the internet and get this Ponketi resource. Okay, then after that, we have a sample text here. Tokenization is crucial for NLP models, and then here we are calling the word tokenize function that we've imported from NLTK.tokenize, and this is the function that would be able to tokenize any given text into word level. And if we run this, we see that let's wait and see. Okay, so it's saying that the sentence tokenization is crucial for NLP models has been tokenized into individual words. Tokenization is crucial for NLP models, isn't it? Thank you very much. For the character level tokenization, I think this is trivial. We simply have our text here. Tokenization is crucial for NLP, and we're simply using list. List is a very popular function it's a popular data structure in Python, and you can use the list function here to convert the strings into a list of characters. In Python, strings are sequences of characters, and then using this list function would now break the strings into individual characters, and then when we run this code, we see the results without any problem. As you can see, the character levels are TOKE, so it has split each and every character in this particular textual information into the individual characters. Let's now go to subword level tokenization. Subword level tokenization, as we've seen in class, has several types. We'll start with the first one, that's the byte pair encoding BPE. So as we've seen in the class, the byte pair encoding tokenization usually works by dividing words into subwords, okay? And then it tries to
balance between the word level tokenization and the character level tokenization. So we start by importing tokenizer, the one with the capital T, from tokenizers. Okay. So the tokenizer class is imported from this particular tokenizers. So this function is imported from this particular class. Okay. And then it's basically a library designed for fast and efficient tokenization in NLP, just like NLTK that we've seen. And then, of course, we load a pre-trained BPE tokenizer, okay, and it is this function that does that, tokenizer dot from pre-trained open bracket GPT-2. So this particular piece of code loads a pre-trained tokenizer that is specifically designed for GPT-2, okay? It's specifically designed for GPT-2 model. And I think we mentioned in the class that it uses the BPE tokenizer. It uses the byte pair encoding as its tokenization method. Okay, so next we have our encode function here. Okay, we have our encode function here that is used to tokenize the input text. Which text is that? That's tokenization is crucial for NLP. And if we do that, it will split the text into subword units using the pre-trained BPE model. So if we run this, okay, you can see the result. The byte pair encoding has been able to split this particular tokenization into this, okay? Token, you can see that the word token, which in word level tokenization would be a single word, has been now split into two, tokenization. And then we have is crucial for NL for, you can see N separated, and then we have LP, and then we have our models. In the results, you notice some funny letter here, G here. Okay, here. So what does that mean? This special character, something like a G with a dot on top of it, indicates that there is a space before the word. Okay? And if you look carefully, you see that for this one, there is no that G because there is no space before, it was tokenized. It just follows this particular word. But because there's a space before this, it's telling us that there's a space before that particular word. So this is basically how the tokenizer marks word boundaries. It's very important for after performing tokenization that we know the word boundaries. So for this particular tokenizer, this is how it marks its own boundaries when it's tokenizing subwords. Okay, basically telling you that there's a leading space in the original sentence before that particular word. Okay. So in short, we've seen that this word token has been now split into two, token and ization. Okay, and then we have is separately. This G just telling us that there is a space before this particular, there's a space before we have the word tokenized. Okay, but for LP, you can see that there is no space, and that's why we don't have any particular issue. Here we are using a pre-trained tokenizer. Basically you train this on a series of words, but here we are simply trying to train based on a training sample. So if you don't like to use a pre-trained tokenizer, okay, you can decide to train your own. Okay, so we're assuming that you have some data set, okay, maybe some textual information in a particular text file containing several words, and then you want to now use that corpus to tokenize a particular sentence, isn't it? For example, here I'm just using this simple corpus as an example, but in reality, we are to use several myriad of text corpus for us to be able to train a very reasonable tokenizer from scratch. Okay. So as usual, this is where we imported the tokenizer, and then we are going to be using this particular function BPE from tokenizers.model. Okay, this is the byte pair encoding model that we use for our tokenization. And also we imported this BPE trainer, okay, because like I said here, we are not using a pre-trained model. We are not using a pre-trained model. We want to now use our own training data to tokenize our text. So the BPE trainer is imported from tokenizers.trainers, and it is the one that is responsible for training. Okay, we use it to train the BPE tokenizer on a given corpus of text. But like I said, I'm just illustrating this, so I used a very simple text. So I'm just assuming that this is the text I want to use to now train my tokenizer so that I can now be able to tokenize this particular sentence. So we begin by initializing the tokenizers and trainers. This particular code, tokenizer, open bracket, BPE, it's just creating an instance of the BPE tokenizer, okay? Basically, if you do object-oriented programming, you know that if you have a class, you have to create an object of that particular class, okay? So it's the object that will perform the byte pair encoding tokenization, okay? And then here we have trainer is equals to the BPE trainer, where we call the BPE trainer that we've imported earlier, okay? So here the BPE trainer is initialized with a list of special tokens. We have the onc, the CLS, the SEP, pad, and mask. So these special tokens are typically used in NLP tasks like classification or question answering, amongst others. And their role is to handle unknown tokens. We've seen this one, ONK, in the class. We said if the token is unknown, then we have ONK, isn't it? Or if we want to perform, let's say we want to pad, okay, if you want to pad that particular sequence, or maybe if you want to mark the start and end of a sequence, okay. So these are just initialized parameters to this particular BPE function. And of course here, this is the training corpus. That's our data. That's a small training data that's defined here, consisting of some example sentences. So the tokenizer is going to learn to split the text into subword units based on the frequency of character pairs in this particular corpus. If you recall from the class, we said we have to list all of the pairs in the we have to list all the words in that particular corpus and count their frequency. Okay, so the tokenizer is going to learn to split the text into several subword units based on the frequency of the character pairs that appear in this particular corpus. So just for explanation, we are using a very simple text corpus. This is the code that does the actual training. Okay, you can see train from iterator, and if in doing that you feed in both the training data and the trainer. Okay, our corpus is simply this simple text, just for illustration, and our trainer is what we've given here, isn't it? It's going to be based on the byte pair encoding, and then of course this is the code that does the actual tokenization. Okay, is the code that does the actual so that given text, for example, if we want to tokenize natural language processing, okay, so it's this particular code that's used to extract the list of subword tokens that's produced based on the BPE model. Okay, so let's just try to run this. But like I said, we are using a very simplistic example, so it might not really be so comprehensive as what you see. So if you look carefully, you notice that the sentence natural language processing has been tokenized into natural language process, and then we have ING here. So based on the corpus that we use in training, It means the tokenizer might have learned that the word natural, okay, the word natural and the word language should stay as a whole, isn't it? And that's why you're seeing it together, isn't it? So it's saying that the word natural and language should stay as a whole because these are frequent enough in the training corpus. And also the word processing was split into two subwords, that's process and ing. So this split is due to the frequent occurrence of these subword units in the training corpus. As you can see, we have several ing. Okay, we have ing here. Okay, we have ing. We have ing here. So probably it has learned that ing has a specific meaning, and then it is what being tokenized separate from the word process. Let's now move to word piece tokenization. We've looked at byte pair encoding. The next one is word piece tokenization. So we've explained in the class that word piece tokenization is very similar to byte pair encoding, but it has its own unique way of managing subwords. Okay, and it's tokenizing based on the corpus it was trained on, isn't it? And the ability to handle out of vocabulary words is a very crucial part of, let's say, transformer-based models like BAT. And WordPiece provides a robust solution for this type of problem. So this code demonstrates how WordPiece tokenization is performed. And then let's take the code one after the other. Here we imported the BAT tokenizer first. It's a class from the transformers library, as you can see. And this class is specifically designed for the fast tokenization with BAT models and supports the word piece tokenization method, just like we've seen for the GPT-2 with respect to BPE. Okay, and then here is where we loaded the BAT based on case. Okay. The BAT based on case refers to the base version of BAT, and it uses lowercase tokens, and it was trained on a large corpus of English text. Okay, and the word piece tokenizer works by splitting words into subunits, especially useful for handling rare or out of vocabulary words. Okay, so the next is the tokenizer, where we tokenize. So this is the particular code that does that. And the key function is this particular function, tokenize from the tokenizer class. Okay, so basically it's the key function that's used to tokenize the input text. And like we mentioned, it's very straightforward. It splits the input into subword tokens using the word piece algorithm. Okay, and basically it will break the sentence into smaller subword or characters if necessary. And like we mentioned, it is particularly useful because it can represent out of vocabulary words by breaking them into known subword units. So at this point, let's now print. We printed the result, and if you run the code here, we are going to see the output. Let's wait and see. So if you see carefully, you see that this is tokenization, but the word token and ization were split into two parts, okay, the token and the ization. And like we mentioned, this particular prefix, the double hash prefix here, indicates that the subword tokenization is a continuation of the previous token here, isn't it? So it's saying that this ization is a continuation of the word token. Okay, and we also have is crucial for NLP. You see, we have the NL and then we have P. The P here has also been tokenized, and then it's saying that it's a continuation from the other, and this is how it does the tokenization in a very nice way. Let's now go to the last one, which is sentence piece tokenization, because in the class we treated three. We treated the BPE, the word piece, and the sentence piece. Okay, as usual, we start by importing this particular auto tokenizer from transformer. Okay, so the auto tokenizer class is imported from the transformer library, and it's a flexible and a very generic tokenizer that tries to automatically load the appropriate tokenizer for any pre-trained model in the Hugging Face model hub. Okay, and as you can see here, we are loading a pre-trained sentence tokenizer based on T5 small. Okay, T5, even though we are going to come to it in our later class, is a model. It's called why it's called T5 is because the name has 5 T's. It is called text to text transfer transformer. Okay, text to text transfer transformer. So it's a model that uses sentence piece tokenization. Okay, and like we mentioned, it's a data-driven subword tokenization method that doesn't require predefined vocabularies and can be applied to any text. The tokenize here, okay, the tokenize here is the method that's used to break the input sentence. Tokenization is crucial for NLP models, and it's used to tokenize this particular sentence into subwords. Okay, and if you recall, we said sentence piece tokenizes the text based on learned subword units, which could be characters, word pieces, or other segments based on the model's training. And at this point, we are simply printing the tokens that we have tokenized here. And then if we run this, we see the result. So from the result, you can see that the word tokenization here has been split into what? Has been split into token and ization. Okay? And of course, we told you that the symbol here, this underscore, okay, that occurs at the beginning of a token indicates that there is a space before the word in the original sentence. So for example, let's carry is. Okay, there's a space before is, so we have an underscore here. For crucial also there's a space. Okay, for also there's a space, and then for the NLP was split into two. There is N, but for the N, there's a space before the N. However, for the LP that was tokenized, there is no space, and that's why it was left like that, telling you that it's just linked to the previous token. And so also models was tokenized into models with an underscore before it, and then the full stop at the end of the day. And like we mentioned in the class, just as a final note, sentence piece is particularly useful when you are dealing with a large variety of languages or tasks, especially where it is hard to define a fixed vocabulary in advance. I think at this point we've come to the end of the lab, and I want to believe that you have a good appreciation of the various tokenization methods, from the basic sentence level tokenization, word level tokenization, to character level tokenization, to even subword level tokenizers, specifically using byte pair encoding, BPE, word piece tokenization, and sentence piece tokenization.
So as always, let's have a quick recap of the key points that we've covered. We've seen that tokenization is the foundation of NLP, which simply breaks text into manageable units. Okay, and we explored word level tokenization, where we split text into individual words. We also looked at character level tokenization, which involves breaking text into individual characters, useful for fine-grained analysis. We also looked at subword level tokenization, which is a powerful method to handle unknown or rare words. We also looked into subword level methods, including byte pair encoding, BPE, word piece, and sentence piece, amongst others. We've seen that BPE merges frequent character pairs while word piece split words into meaningful subunits and is used in models like BART. Sentence piece and unigram models are language agnostic approaches for tokenization. Okay. And a memorable takeaway from today's session is that choosing the right tokenization method depends on the NLP task and the nature of the dataset. To ensure you are practicing, as always, I've prepared an assignment for you. The objective is to evaluate and compare different tokenization techniques on a dataset. And the specific task is that you apply word level, character level, and subword level tokenization to a given text. And then you should be able to explore byte pair encoding BPE, word piece, and sentence piece subword tokenization methods using Python libraries. You should also compare the output of each technique and discuss the advantages and limitations of each particular method. Please upload your submission to the learning portal. These are some resources for further reading. In our next class, we shall look at Transformer Architectures Part 1. Thank you very much for having me.
Well done on completing today's class. Let's quickly recap the key points we've covered. We started by discussing tokenization and its importance in breaking down text for NLP tasks. We explored word-level tokenization, which involves splitting text into individual words, character-level tokenization, which involves breaking text into individual characters, useful for fine-grained analysis. We also explored subword-level tokenization, which is a powerful method for handling rare or unknown words. We also dived into subword-level methods, including byte pair encoding BPE, where we merged frequent character pairs, word piece tokenization, which involves splitting words into meaningful subunits used in models like BERT. We also covered sentence piece and unigram models, which are language agnostic approaches for tokenization. A memorable takeaway from today's session is that choosing the right tokenization method depends on the NLP task and the nature of the dataset. To ensure you're practicing and applying what you've learned, I have prepared an assignment for you. Upload your completed assignment to the learning portal. The objective is to evaluate and compare different tokenization techniques on a real-world dataset. The full assignment details will be available on the learning portal. If you have any challenges, reach out to the teaching assistant or ask for clarification in the discussion forum. Thank you for being an active learner in today's session. Keep pushing your boundaries, and I look forward to seeing you progress in the next class. See you soon.